In this video, we solve problem 3.6.2 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to consider the IVP given below. We have y prime equals -1/5 of y, and y of x naught equals, or y of 0 is equal to 6. We're asked to show that when Euler's method is used to approximate the solution to this IVP, initial value problem that is, at x equals 9, then the approximation with step size h is given by 6 times the quantity 1 minus h over 5, all raised to the 9 over h power. First, we're asked to apply one iteration of Euler's method in order to write the next term y sub n plus 1 in terms of x sub n, y sub n, and h as needed. So they're actually not telling us what the step size is, but we know that we want to get from x equals 0 to x equals 9, and we want to find out what the approximate y value would be at x equals 9 for various step sizes. So we might have h equals 1 and we'd take 9 steps, or we might have h equals 1/10 and we'd take 90 steps. But this is telling us that the resulting approximation will be given by this, where h is that step size that we chose. Now they're actually walking us through showing this. Normally, if this was a question on a test or a quiz, it would just say, show that when Euler's method is used to approximate the solution at this x value, that the approximation with step size h is blank. And then you would just have a text box or a piece of paper, and you would explain why applying Euler's method would get you to this result. But when you're doing this in MyLab Math, they are outlining the method for you and they want you to sort of fill in the blanks. So that makes this problem a little bit hard in the sense that you don't know exactly what it is they're looking for, but you know that you're trying to get from this to this. But that's what this video is for. I want to show you kind of what they were expecting and what they were looking for. So as you proceed through the problem, the next thing that pops up on MyLab Math is this. It says, apply one iteration of Euler's method in order to write the next term y sub n plus 1 in terms of x sub n, y sub n, and h as needed. Now, remember how Euler's method is designed. It's basically saying, let's use the tangent line at the point x sub n, y sub n to find y sub n plus 1. That's what we're doing here whenever we're applying Euler's method. And so what that means is that the change in y over change in x is equal to the slope of the tangent line at that point. Well, whenever you have a differential equation, a first order differential equation like this, where y prime is by itself, this function on the right-hand side gives you the slope at any particular x sub n, y sub n. So if we call this f of x, y, at x sub n, y sub n, the slope will be f of x sub n, y sub n. Now the change in x over change, or change in y over change in x is going to be this. Your original x value, or your original xy pair is that x sub n, y sub n. And your new xy pair is going to be called y sub n plus 1 and x sub n plus 1. So if we're looking at a graph of this, let's say after n iterations, we're right here, and this is x sub n, y sub n. Well, we draw a tangent line with the slope given by f of x sub n, y sub n, because we know that the slope of the solution curve should be given by f of x sub n, y sub n, just plugging in that point, which we know is on the solution curve, into the right-hand side of that differential equation. And then we say, okay, if we go a little step like this, h, in the x direction to get to x sub n plus 1, we're going to say that the y value right there is probably on our solution curve. That's going to be our approximation of the solution. We're going to call that y sub n plus 1. So this x sub n plus 1 minus x sub n is going to be given by h. And sorry, I didn't quite leave myself enough room for all this. If we multiply both sides by h, we get this. And then if we solve for y sub n plus 1, we have that y sub n is equal to or y sub n plus 1 is equal to the original y value, or the y value at the last location, plus the slope at that last location times the step size. So that's what goes in over here. That's what they're asking for. The original y value plus the slope times the h, which is the step size, or you can think of it as change in x. So it's like we're taking this, which is an approximation of the change in y over change in x, and we're multiplying by a change in x. So that's giving us a little change in y. This says that the new y value is equal to the original y value, or the old y value, plus the change. And I think that makes sense. If you take the original y value and add the change in y, you should get the new y value. Okay, so then in the second part of this question, it says, now substitute f of x sub n y sub n equals negative 1/5 y sub n into the previous form. So basically all they're having you do is replace this function right here, f of x sub n y sub n, with the appropriate expression given this differential equation. Well, the slope at x sub n y sub n, according to this differential equation, is negative 1/5 of the y value. So that's negative 1/5 of y sub n. That's all they want you to do here. So they're saying y sub n plus 1 is equal to y sub n plus that slope, which we know to be negative 1/5 of y sub n because of the right-hand side of the differential equation, times your h. Now you could leave it like this, but you notice that this term and this term have a y sub n in common. So you can factor out a y sub n from those. Y sub n times 1 gives us the first term, and y sub n times a negative 1/5 h gives us the second term. And then you might even write this differently, knowing that we're trying to get to this form where we have the 1 minus h to the, or 1 minus h over 5 inside the parentheses. Multiplying h by 1/5 is the same as dividing h by 5. So we'd have y sub n times the quantity 1 minus h over 5 right here. And that's equal to y sub n plus 1. So that is our answer for that part. Okay, then the next part, let me write that down and then I'll start the recording again. So the next part of the problem statement says, use this recursive relationship to write a term k steps into the future, y sub n plus k, in terms of x sub n, y sub n, h, and k as needed. And so they give you y sub n plus k equals blank. Well, I think the easiest way to figure out what this is to just look for a pattern. We start with y sub 0, and then y sub 1, according to this formula, is the last y value, which is y sub 0, times 1 minus h over 5. And then y sub 2, according to this, is y sub 1 times 1 minus h over 5. But y sub 1 was all of this. So what we have is y sub 0 times 1 minus h over 5 times 1 minus h over 5. So that gives us y sub 0 times 1 minus h over 5 squared. We've got two of them. And then we keep going. Y sub 3 is the last y value. That's y sub 2 times 1 minus h over 5. And y sub 2 was y sub 0 times 1 minus, whoops, I don't know why I switched colors there, 1 minus h over 5 squared. Well, I guess I knew it. Anyway, so that's our y sub 2. And then we're taking that and we're multiplying by 1 minus h over 5. I see now why I was switching colors, because I was trying to be consistent with that pattern. But now I've got 1 minus h over 5 squared times another one. So that means I've got 1 minus h over 5 cubed. Okay, and so now we're looking for a pattern. We're saying, what's the relationship? And I think you can tell what the relationship is. To get from y sub 0 to y sub 1, we multiplied by 1 minus h over 5. And then we did that again, so that when I look at this formula, y sub 2 has a 1 minus h over 5 squared, and y sub 3 has a factor of 1 minus h over 5 cubed. Y sub 1 has a factor of 1 minus h over 5 to the first. So with that, we see, well, that y sub n is equal to y sub 0 times 1 minus h over 5 to the nth power. Because if that subscript is 3, that exponent is 3, because we've multiplied by 1 minus h over 5 3 times. So if we've done this n times, we've multiplied by 1 minus h over 5 n times, and y sub n is equal to this. And then you might say, okay, well, how does that relate to y sub n plus k? Because that's what they wanted, was y sub n plus k. Well, y sub n plus k, according to this, is y sub 0 times 1 minus h over 5 raised to the n plus k. But I'm not supposed to have my y sub n plus k in terms of y sub 0. I'm actually not even supposed to have it in terms of n. We want it in terms of y sub n, x sub n, h, and k is needed. But that's easy enough to do because we can break this up into two pieces. We can think of this as y sub 0 times 1 minus h over 5 to the nth times 1 minus h over 5 to the k. And this piece, well, that's y sub n. So y sub n plus k is equal to y sub n times 1 minus h over 5 to the k, which I think makes sense because you started with y sub n and then you multiplied by 1 minus h over 5k more times in order to get to y sub n plus k. Okay, so we've answered that part of the question. We're still not quite there yet, but they're going to lead us through the method and tell us what to do next. Okay, so then it says, in order to finish the problem, for the approximation in question, write the number of steps that are needed in terms of the step size h. Well, remember where we started and remember where we're going. We're starting with x naught equals 0, and we're trying to get to x equals 9. Well, if I'm trying to cover that distance, I just need to take the distance between x equals 0 and x equals 9, which happens to be 9. And then I will divide that into h pieces. So, or not h pieces, how can I say this? Divide that by h to get the total number of steps, if that makes sense. So we're going to say the total number of steps, that's k, is equal to the total, I'm going to say distance that we need to cover. Divided by the step size. Because if I were to take this equation and multiply both sides by the step size, the total number of steps times the step size should give me the total distance covered. Well, the total number of steps is given by k. The step size is what we're calling h. And the total distance covered, well, if we're going from x equals 0 to x equals 9, it's going to be 9 minus 0. In general, if that was x equals a to x equals b, that would be b minus a. So we're going to take 9 and divide by h. If h equals 1, we need 9 steps. If h equals 0.5, then we're going to need 18 steps because we're going half a unit, half a unit, half a unit. We're going to have to go twice as many steps. If h equals 0.25, well, then you're going to have to go 36 steps. Hope that makes sense. Okay, so then they say, thus the approximation k equals h over 9 steps after y naught equals blank. And that was given in the problem statement. Remember, x naught is our 0 here, and y naught is the 6. Is, and they have 6 times 1 minus h over 5 raised to the 9 over h. Now that comes from taking these two pieces and substituting into our answer that we got over here. So we had y sub n plus k is equal to y sub n times 1 minus h over 5 raised to the k power. So if we're taking k steps, this many steps after y naught, so we're saying n equals 0 here. We substitute in y naught, and we multiply by 1 minus h over 5 to the k, where k is replaced by 9 over h. And then we say, well, what is y naught? In this case, it's 6. And so that would give us a formula for the approximation of the solution at x equals 9 that depends on the step size. So we could let the step size be 1 or 0.5 or 0.05. And depending on the accuracy of our calculator, I mean, if it's sort of saving the fractions for us rather than decimal approximations, most of the time it's saving a decimal approximation. If it was saving our fractions, we could just sort of drag and drop in Excel. But I don't think Excel saves those fractions. I think it only saves a certain number of decimal places. But this is the formula that we could use to see what our approximation would be as that step size gets smaller and smaller. And we know that we tend to expect the approximation to the solution to get better as the step size gets smaller.